On this question, we want to use L'Hopital's rule to evaluate the limit. The limit as x approaches infinity of 5x squared minus 4x plus 1 over 2x cubed plus x minus 7. So we're going to start with direct substitution. And if we try to evaluate this limit with direct substitution, we would have 5 times infinity squared minus 4 times infinity plus 1 over 2 times infinity cubed plus infinity minus 7. And that's going to end us up with infinity over infinity, which is one of our indeterminate forms. So because we have this indeterminate form of infinity over infinity, that allows us to use L'Hopital's rule. So with L'Hopital's rule, we would calculate the derivative of the numerator and calculate the derivative of the denominator and then apply the same limit. So doing that, we have the same limit as x approaches infinity. If we calculate the derivative, that would be 10x minus 4, that's the derivative of the numerator, and the derivative of the denominator would be 6x squared plus 1. Notice I'm not calculating the derivative of the whole function because we would need to use the quotient rule if we were doing that. So L'Hopital's rule says calculate the derivative of the numerator and the derivative of the denominator individually and divide those. Then we try to use direct substitution again. So we have 10 times infinity minus 4 over 6 times infinity squared plus 1. And once again, we get that indeterminate form of infinity over infinity. However, we can use L'Hopital's rule again. So we're going to do the same limit as x approaches infinity. Calculate the derivative of the numerator to be 10. The derivative of the denominator would be 12x. And now when we use direct substitution, we get 10 over 12 times infinity. That's 10 over infinity. And we know that if we have a fixed value in the numerator and our denominator goes to infinity, that means this overall fraction is approaching 0. So using L'Hopital's rule, we found that the limit as x approaches infinity of 5x squared minus 4x plus 1 over 2x cubed plus x minus 7 is equal to 0. In this question, we want to evaluate the definite integral. And that definite integral is from pi over 3 to pi over 2 of cosecant squared x. So since we have a definite integral, we're going to use the fundamental theorem of calculus. And the fundamental theorem of calculus says if you have a definite integral from a to b of f of x dx, then you can solve this definite integral by finding big F, that's the antiderivative of lowercase f, and then you're going to evaluate at the bounds. And the way you evaluate is by evaluating the upper bound and then subtracting the evaluation of the lower bound. So this is the fundamental theorem of calculus. For our example, we need to find the antiderivative for cosecant squared x, which is negative cotangent x. And then we need to evaluate that on the bounds from pi over 3 to pi over 2. So we'll start by evaluating at the upper bound. That's negative cotangent of pi over 2 minus, we need to evaluate at the lower bound, negative cotangent of pi over 3. So then to simplify this, we would have negative cotangent of pi over 2 plus cotangent of pi over 3. And we need to think about our unit circle. So on our unit circle, we need to look at the values of pi over 2. Pi over 2 is an angle of 90 degrees, and that ordered pair is 0, 1. So that's pi over 2. And then an angle of pi over 3 is here, which is 1/2 square root of 3 over 2. And then we also need to know the definition of cotangent of an angle. Cotangent of an angle for the unit circle is the x over the y, the x coordinate over the y coordinate. So on the first one, negative cotangent of pi over 2, we're going to use that x coordinate of 0 over the y coordinate of 1. And then for cotangent of pi over 3, we'll do the x coordinate of 1/2 over the y coordinate of square root of 3 over 2. So negative 0 over 1 is 0. For this dividing fractions, we'll multiply by the reciprocal. That's 1/2 times 2 over the square root of 3. Those 2's cancel out. And we have 1 over the square root of 3. We can leave our answer like that, or you could rationalize by multiplying by square root of 3 over square root of 3, and that would give you square root of 3 over 3. So we have our definite integral of pi over 3 to pi over 2, cosecant squared x dx being square root of 3 over 3. For this question, we want to discuss the continuity of the function, state the interval where the function is continuous, and whether the discontinuities are removable or non-removable. So in this example, we have a piecewise defined function. F of x equals 3x minus 4 when x is not equal to 1, and f of x is 2 when x is equal to 1. So we want to find whether this function is continuous. Now, if I think individually on these equations, this equation 3x minus 4 is a linear equation, and that is a category of polynomials. And so on this individual function, it will be continuous. And then this 2 would be a constant, a horizontal line at y equals 2, and it will be continuous if we think about it individually. So both of these equations are continuous functions individually. They would be continuous from negative infinity to infinity. However, when you put them together in this piecewise defined function, we've got to see if the pieces match up with each other to create a continuous function. So as we look at our conditions on the right here, this is going to help us understand where we need to look to decide if these pieces match up with each other. We use the first equation anytime x is not equal to 1, and the second equation when x is equal to 1. So this is the location at x equals 1 where we're concerned about whether the two pieces line up with each other. So we're going to take a look at the continuity criteria. We're looking for where the function is continuous, so we'll look at the continuity criteria at the value of x equals 1. So there are 3 criteria for a function to be continuous at a point. So the 3 criteria are: number 1, the function is defined at that value. F defined at that point. Number 2 is that the limit exists at that point. And then number 3, the limit must equal the function value, the function definition at that point. The limit at that value must equal the function at that value. So this first one is f of c being defined. This one is the limit at x equals c of f of x exists. And then the final criteria is that they have to equal each other. So we're doing that for a value of 1. We need to see if f of 1 is defined. We need to see if the limit as x approaches 1 exists. And then we need to check to see if those two equal each other. And that will tell us whether this function is continuous at x equals 1. So we'll start with f being defined at 1. So f of 1, we're supposed to use the second equation when x equals 1. So that means f of 1 is 2. So the function is defined at x equals 1. Then we need to see if the limit exists. Now, usually with these piecewise functions, it's really helpful to look at the one-sided limits to figure out the overall limit. So, in order to figure out the limit as x approaches 1 of f of x, I'm going to look at the limit as x approaches 1 from below, and then the limit as x approaches 1 from above 1. And as long as these two equal each other, then I know the overall limit will equal that value. So let's start with figuring out the limit from below 1. We need to decide which one of these equations to use. I know that I use the second equation when x is equal 1, but I'm finding the limit for 1 minus. That is below 1. For every other value except for 1, I'm supposed to use the first equation. So I'm going to use the first equation to calculate this limit. I have the limit as x approaches 1 from below of 3x minus 4. We use direct substitution to get 3 times 1 minus 4, and we get negative 1. So the limit as x approaches 1 from below of f of x is negative 1. And then the same thing happens when we're doing the limit from 1 plus. So above 1, we should be using the first equation, because we use that first equation for every value of x except for 1. So we get the limit as x approaches 1 from above. We're using the first equation based on the conditions. We'll solve this with direct substitution. 3 times 1 minus 4. We get negative 1 again. So because the one-sided limits do equal each other, that means the overall limit is equal to negative 1. So far, we know that the function is defined at 1, the limit exists at 1, and then we need to do the final check of whether the limit agrees with the function value. Remember, we got negative 1 for this limit. So you can see that the function value is 2, and the limit is -1. And so our final criteria for being continuous didn't hold up. So we know that we have a discontinuity at x equals 1. Otherwise, the function is continuous. So the function is continuous on the interval from -infinity to 1, union with 1 to infinity. So we have that one discontinuity, and the last thing we need to do here is decide if that function, if that discontinuity is a removable or non-removable discontinuity. So we want to remember the difference between these two. For a discontinuity to be removable, you need to be able to change one point of the function to create a continuous function. So if you are able to fill in that discontinuity at x equals 1 with a single point and create a continuous function, then you would say that discontinuity is removable. If you can't do that, then we put it in the other category of non-removable. So this is really whenever we have a hole in the graph is when we consider the discontinuity to be removable. And that is exactly what's happening in this example. Because we just have a single point, a single x value that is different from the rest, that's creating a hole in the graph. Just to give you an idea, we can sketch the graph quickly. 3x minus 4 is a linear equation with a y-intercept of -4. We can plot that y-intercept. We can do our rise over run, rise 3, run 1. That will give us our line. However, at that one value of x equals 0, we need to put a hole there. And instead of that point, we have y equals 2 at that value. So if we were able to get rid of that one point and fill in that discontinuity, we would have a continuous function. So we would categorize this discontinuity as removable. So just want to make sure we've answered everything. We want to discuss the continuity, which means to state where the function is continuous. The function is continuous on all real numbers except for x equals 1. That's -infinity to 1, union with 1 to infinity. We stated the discontinuity as x equals 1, and the type of discontinuity is a removable discontinuity. So on this question, we want to find the equation of a tangent line at the point 1, 1 for the equation y equals -3 over x squared minus 4. So in order to find the equation of a line in general, using algebra, we typically would use the point slope form, which is y minus y1 equals m times x minus x1. And m stands for the slope of the line. And then we have an ordered pair that is on that line, x1, y1. So that is a point on the line. So we're given this point 1, 1, which is a point that's on this line. It's on this curve, y equals -3 over x squared minus 4. And so that 1 will be our x1, and that 1 will be our y1. So the thing that we're missing here is the slope of the line. So we're going to use calculus to find the slope of the line, because the derivative is the slope of the tangent line for any point on the line. So we want to take our equation, y equals -3 over x squared minus 4, and calculate the derivative. But before I calculate the derivative, I'm going to rewrite it in a format that might be a little bit easier to calculate the derivative. That's -3 over x squared minus 4 to the -1 power. So if you leave it in the original form, you have to use the quotient rule to calculate the derivative. But if you change it to this form that I've written here, you do have to use the chain rule. So it's up to you about whether you want to leave it in the original form and use the quotient rule, or change it to this form and apply the chain rule. So I'm going to calculate the derivative with the chain rule. So with the chain rule, I'm going to carry down that constant multiple of 3, and we would first calculate the derivative on the outside. That's using the power rule, so we bring that power down and take 1 away from the power. And then we're leaving the inside alone and multiplying by the derivative of the inside. So the derivative of x squared minus 4 is 2x. And then I can simplify this derivative. -3 times -1 is a +3. Multiply that by 2x gives me 6x in the numerator. And then I can bring that x squared minus 4 squared down to the denominator. So then I need the slope. This derivative is the slope at any point, but we're interested in the point 1, 1. So we want to evaluate this derivative at an x value of 1. So for x equals 1, that derivative will be 6 times 1 over 1 squared minus 4 squared. That's 6 over -3 squared. That's 6 over 9, which reduces down to 2 over 3. So we have a slope of 2/3. And now that I have that slope, I have everything I need to create the equation of the tangent line. So my formula is y minus y1 equals m times x minus x1. That's y minus 1 equals 2/3 times x minus 1. I usually like to write the tangent line in slope-intercept form. So I'll distribute that 2/3, get 2/3 x minus 2/3. I'm going to add 1 to both sides, and that gives me y equals 2/3 x, and I need to combine these together, so I need them to have a common denominator. So that's -2/3 plus 3 over 3, and that's 1/3. So we have the equation of the tangent line at the point 1, 1 being y equals 2/3 x plus 1/3. Thank you for checking out my videos. Have a great day.